Hey everybody, Mr. Klein here to do a little bit of indefinite integrals with you. These problems are going to be coming straight out of page 202, one of my favorite numbers, in your Forrester textbook. And you've been assigned the odds. Specifically, you're doing 1 through 31 odd. What I'm going to do here is I'm going to do the evens. Now, the idea is that all of the even problems are repeats of the odds. So for instance, I'm going to do number 2. And this should be really similar to doing number 1, which you were going to do. And then I'm going to do number 12, which should be similar to number 11. I'm going to do 14, which should be similar to the one right before it, number 13, and so on. Okay. So the first thing that you need to know is this. Indefinite integrals, which will look like this. You'll see the little summation symbol, and then you'll see a function right here, and then you'll see a dx. An indefinite integral is the same thing as an antiderivative. What that means is that the summation symbol and the dx, you don't do anything with them. They're just a message that is telling you to take the antiderivative of this function. So in this case, I would say the degree needs to be popped up by 1 using the power rule. And then I'm going to multiply by the reciprocal of 21 in order to balance it out. And my antiderivative looks like this. Remember, you can always do a quick check. So if I take the derivative of this, 21 comes down and cancels with this 21 to give us a 1. Degree goes down by 1 to give us a 20, and we are good. Okay. Let's do another one. Let's do number 12. Number 12 is an exponential function. And I know that it's exponential because look right here. See how that x is in the exponent? That's the giveaway. Recall that the derivative of any function that has x in the exponent will be the exact same base to the power, but with a constant. And that constant is the natural log of the base multiplied in front of it. So a good guess anytime you've got something like this is the exact same thing. Okay, so that's going to be my guess. Now, if I actually take the derivative of my guess, that would be natural log of 8.4 multiplied by 8.4 to the x power. So as I look at the derivative of my guess, I can see that it's got this extra term right here. So I'm going to multiply by the reciprocal of that term, or 1 over that term, and that will give us our answer. Okay. Move it along. Let's go to number 14. Number 14 is the first one where you're going to use the chain rule. And of course, our sort of sign that we're going to be working with chain rule is that we have an inside and we have an outside function. And anytime we know that this antiderivative is the result of a chain rule, a good guess is to deal with the antiderivative of the outside function. So I'm going to say I think the outside function, the power should be knocked up to 6. And I'm going to leave the inside function alone, plus c. And then I am going to test this. If I take the derivative of this function, I get 6 times the inside to the 5th power, multiplied by the derivative of the inside, which is 3. So we notice that there's a 6 and a 3 here that we don't really want. So I'm going to divide this by 18 to cancel that out. And that gives us our answer to number 14. Again, if you had any trouble with number 13, this should help. All right, let's do another one of these. Here's our first one that involves trig. This one looks to me like the result of a chain rule as well. As you can see that we have an inside function. We have an outside function. And then we have this thing right here, which is like the derivative of the outside function, or the inside function. I misspoke there. So just like on the last problem, we say our outside is something to the 8th power, which means that a good guess would be something to the 9th power. And we take the inside function, we leave it alone. So antiderivative of the outside, leave the inside alone. Do nothing with the leftovers right here. And let's see how our guess goes. If I take the derivative of this, I would get 9 times the cosine of x to the 8th power, multiplied by the derivative of cosine, which we will recall is not sine, it is the negative sine of x. Now, it's important to notice that negative because we don't have a negative here. We're going to have to compensate for that. I'm going to say, well, there's a 9 and a negative. So this would be a negative 1/9. And there's our answer for number 18. Okay. Moving on to number 22. Now, number 22, I'm going to do this one with you because there are parentheses here. And we're tempted when we see parentheses to think chain rule. But this one is not a chain rule because the parentheses are to the 1st power. And raising anything to the 1st power doesn't change it. It means it's not really a function. So when you see one like this, you're just going to think of it as having 1, 2, 3 separate terms. And we're going to independently take the antiderivative of the first one, and then the second one, and then the third one, and we're going to slap a C on the end. Okay, let's do another one. Now, number 24 is probably the most perplexing problem on this assignment. Or well, I should say 23 is, and this will help you with 23. So if I was you, I would look at this and say, there's an inside, there's an outside. So let's treat this like a chain rule. And that would give us something to the 3rd power. Leave the inside alone. Now watch how this is not going to work. When we test, our test would be 3 x to the 3rd minus 6 squared multiplied by 3x squared. And so the things that are missing are a 3 and a 3, but we're also missing an x squared. And that's a huge problem because you cannot just say, I'm going to divide this by 1/9x squared. You can only divide by constants right here. And let me explain why. If we divide by x squared, suddenly this becomes a quotient rule problem. Think about that. If you were going to take the derivative of this, now you would have to use the quotient rule, and you would get a big, complicated mess that doesn't look like that. So, when you take the derivative, if you get an extra x term, that means that you're going about this all wrong. It turns out that this one, you actually have to change the inside function first by expanding it. And you'll know to do this because the chain rule approach won't work. So if you expand x to the 3rd minus 6 squared, you're going to get something that looks like this. X to the 6th minus 12x to the 3rd plus 36 dx. And now once we get here, taking our antiderivative is just a matter of saying antiderivative of first term, antiderivative of second term, antiderivative of third term, slap a C on it. Let's continue. I'm going to do two more. Number 30 looks like this. Now I see that I'm asked to take an antiderivative that has a cotangent and a cosecant. And I know those go together. And I'm thinking that the derivative of cotangent is negative cosecant squared x. So it might make sense to think of this as being written this way. Cotangent to the eighth, and then here's the leftovers. Okay, so this one's like a chain rule. When you make your guess, you're going to say cotangent x to the ninth plus c. I'm going to tell you that when you actually take the derivative, you're going to notice a couple of things. You're going to notice you need to divide by a 9 and you need a negative. So we're going to throw a negative 1/9 right here. So that one's pretty straightforward. I did that one to impress upon you how this one right here is a little bit trickier. Now, I know that the derivative of tangent is equal to secant squared of x. And that's probably not going to be helpful because this is secant to the seventh, right? So another way that we could think of this is that the derivative of secant is equal to tangent times secant. But in order for that to work, if you try to think of this way, you're going to get in trouble because the inner function has a derivative of tangent times secant, and you've only got a tangent right here. So instead, what you're going to do boop, 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 is take one of these secants that are sitting right here on the inside and loan it to the outside function. In order to get an answer that works on this one, you have to do it this way. See how now it's set up where your inner function has this as its derivative. The answer ends up looking like so. Secant of x to the seventh plus c. I'm going to throw a 1/7 right here. You can check if you take the derivative of this, you will get that. All right, and that is enough of our antiderivatives. Good luck on your assignment.